don't mind that. Okay, so today we're going to talk about what are called redox reactions. And so redox is just the combination of the words reduction and oxidation. And so in these reactions, there are kind of two reactions happening together. And so one species is going to lose their electrons while the other is going to gain them. And then if there are species in our chemical reaction that they're not involved in this gaining or losing of electrons, we call them spectator ions. And so if we are having an exchange of electrons, this means that we're going to have a change of oxidation state, which is just a fancy term for the charge of these species. And so breaking down what each of these terms are, oxidation is the losing. So one species loses one or more electrons. And if you're losing a negative charge, it becomes positive. Then reduction is when you gain electrons. And then therefore you're gaining that negative charge becoming more negative. So you can think of reduction as the charge is getting reduced. So what I'm going to ask of you guys is you're going to have to determine the charges of species that undergo redox reactions. And so this isn't really necessarily brand new for you guys. You've been figuring out charges for ionic compounds before, but where we originally, the way that we're going to want to approach redox reaction is that, one, we can look up the ions in table E. So this is the polyatomic ions. Or you can just look at the periodic table on your guys' blue packet, and then in the upper right corner is the charge. And then we are going to always use the negative ion or the anion's charge to therefore determine the positive ion. So start with the negative, determine the positive. And this is because we have things like our transition metals that can form more than one charge. And we're not going to know what charge they formed until we figure out what they have to equate to. So we always start with the negative ions. And so, again, you guys already kind of know how to do this, so it's pretty much review here. We can look up in table E that phosphate charge is -3. And so if we know that phosphate is -3, what does that mean iron has to be in Fe3PO42? What? Nope. If this is -3 and there's two of them, what's the overall overall contribution? Is -6, right? So if we need our compound to be neutral and we have 3 irons, this +6 that we need has to be divided among the 3. So each iron's a +2 charge. And so we're going to be doing this. It's just going to be with multiple species in chemical equations. So we'll start with our first example here. So one thing that's nice is that the charges, so I'm going to write the note first to the right here, is that elements by themselves I don't know, I wrote that as 2 words. Hold on. They have a charge of 0, meaning they're neutral. So when we have things like elemental silver and elemental oxygen, like we do for our first example, the charges here are just both going to be 0. Now we have to determine the charges for those elements in silver oxide. And so always starting with our negative charged element, which in this case, they typically is the second element in our formula. So we have oxygen. And if we either use our previous knowledge or look in the table, oxygen likes to form a -2 charge. But now for silver, since we have 2 of them, and I'm not talking about the coefficient up front, We ignore those for determining charges. I'm talking about this too. Since we have two silvers, each of them can only be +1. That way, the compound will still be neutral. And so that's my next note here, is that the sum of the ion charges remain at 0. And so for the next example here, potassium, if it's in its elemental state, what's its charge? 0, easy enough. And then we're gonna work with aluminum sulfate. So if this is supposed to be a subscript 4, so don't mind that typo. But if we look up sulfate in table E, its charge is -2. And so since we have, since we have 3 of them, 3 times -2 gives us an overall -6 from the sulfate ions. That means that everything from aluminum has to be +6, but since we have 2 of them, we have to divide that by 2. Therefore, our aluminum is a +3 charge. Moving on to potassium sulfate. Again, sulfate has a -2 charge, but now we only have 1 of them. So all the contribution from potassium has to equal to -2. We have 2 of them, so potassium must be +1. What about aluminum? What's its charge? 0. Those ones are nice and easy. All right, a couple more examples here. Iron oxide. So what did we say oxygen's charge was? -2. So what must be 1 atom of iron's charge here? +2. If you add them together, it equals 0. And now they're just split up into their elemental states. So the charge is just 0 and 0. All right, and then this next one here, calcium is all up by itself. And then we have hydrochloric acid. And so chlorine typically likes to form a -1 charge. So hydrogen must therefore be a +1 charge. Then moving to calcium chloride. Calcium is chloride is -1. And we have 2 of them. 2 times -1 is equal to -2. And we only have 1 calcium, so it must be equal to +2. And hydrogen gas is an elemental state of 0. So any questions on this kind of review / application to, yeah, go ahead, Evan.
So on like the 3K2 SO4 thing, how'd you get -2?
You'd look that up in table E, because SO4 is a polyatomic ion. Any other questions? Okay. So once you guys are determining the charges, the next step is going to be determining which species got oxidized and which one was reduced. And so this is a review, but it's good to kind of get this down. The species that loses electrons, does it become more positive or negative? Positive, awesome. Becomes more positive, and then is therefore oxidized. Therefore, what's left is saying if you have one that gains electrons, becomes more negative, and then it's reduced. And so I have a little word trick for you guys. This is how I was taught to remember this. But I use oil rig. And what it stands for is oxidation is losing. And then reduction is gaining. So if you never can remember oil rig, you can use that as a tool. And so now we're going to go back through the equations that we just determined charges for, and we're going to figure out which ones were oxidized, what was reduced, and if we have any spectator ions. And so in the first one, we already determined that the charges were 0, 0, plus 1, and minus 2. And so if I follow silver, and so this is a comparison from reactants to products. If we follow silver from the reactant side to the product side, it goes from 0 to plus 1. It becomes more positive. Therefore, this one is oxidized. So I'll write silver as my oxidized, and it goes from 0 to plus 1. That leaves me with oxygen, which goes from 0 to -2. Therefore, O2 was the reduced species, going from 0 to -2. Did we have any other species involved? No, so we just write none. We don't have any spectator ions. Yeah.
So in these ones, you don't have to make the charge equal.
What do you mean? Yeah, you do.
So like on the last page, like you know, it's like a +1 over here. Is that?
Yeah, so there's 2 silvers. A 2. Does that make sense? No, okay. I just want to make sure. All right. So the next one here. So the charges we determined were 0, +3, -2, +1, -2, and 0. And so going from potassium on the left side to the right, we are going from 0 to +1. And so this must mean it's oxidized because it's getting more positive. So potassiums are oxidized species going from 0 to +1. And then if we look at aluminum, it goes from +3 to 0. So it's getting more negative, being reduced. So aluminum is our reduced species going from +3 to 0. Do we have any spectator ions? SO4. Spectator ions mean they are in the chemical reaction, but they don't get oxidized or reduced. And so looking at the charges, SO4 remains at a -2 charge on both sides of the reaction. Therefore, it couldn't have participated. All right, next one here. We have a +2 and a -2 going to 0 and 0. And so if I look at iron, this one's actually being reduced because it's going from a positive number and getting less positive. It's becoming more negative. So iron is going to be our reduced, going from +2 to 0. And then we have oxygen being oxidized as it goes from -2 to 0. And then we don't have any other species, so no spectator ions. Yeah. Yes, because we can't just so the reason being is it's almost ties into the law of conservation. So we can't just throw electrons out into space. So one has to receive from whoever gives. Huh? Oh yeah, you can give multiple. Yeah. So if anybody carries on to chem, you figure out how many electrons are actually transferred towards the end of the second semester of general chemistry. Okay, so next one, we have 0, +1, -1, +2, -1, and 0. So the one that is oxidized is going to be calcium. And then the one that, or I'll write that down. And so calcium goes from 0 to +2. Then we have hydrogen that goes from +1 to 0. Do you have spectator ions for this one? Cl -1. Okay. And one more example here. Aluminum is 0. I don't think we figured out the charges for this one yet. All right, this is a new one. Okay, so carbonate forms a -2 charge, meaning that each silver has to be +1. And then over on the right side, if each carbonate is -2, there's 3 of them, so overall -6, that means aluminum has to be +3, and then 0. So aluminum goes from 0 on the left side to +3 on the right, so that's oxidized. And then silver goes from +1 to 0. And we have another spectator ion, that's going to be our carbonate.